Actually, you can introduce Arun. I can help to ask questions, but you can introduce. Maybe you are preparable.
Um, okay. Hello, everyone. Welcome to CMSA Interdisciplinary Science Seminar. And today we are very happy to have Dr. Arun Debray to talk to us on the topological phase of matter using homotopy theory. And today's talk will also be chaired by outstanding CMSA physicist Dr. Jinwen Wang. So we look forward to hear from them.
So first of all, thanks so much for having me here. It's great to be here. I mean, here being, I'm still in Austin, Texas, but it's great to be at your seminar and to see all of you. So what I'm going to do is I'm going to talk about a mathematical modeling question about modeling these things called invertible topological phases of matter. So from a mathematics standpoint, we don't know how to mathematically formalize these things yet, but we have some ideas, and it turns out that these ideas often involve a lot of the field of math called homotopy theory. So I'm going to try and convey some idea of, okay, well, what are these things supposed to be roughly? How do we get at the modeling question? And so some steps towards considering that. So a key aspect of a modeling question specifically for physics is what symmetries do you take into account? And so for different kinds of symmetries, the problem takes a different form, and the homotopy theory gets more and more interesting. So I'll tell you about different parts of that. A lot of that is due to Dan Freed, who is my PhD advisor, and Mike Hopkins, who is in Boston, and then part of it was my PhD thesis. So hopefully I'll get to tell you about that. So some of you may be looking in the upper left corner and thinking, that's a lot of slides. That is more than 2 per minute if I don't run over. But first of all, a lot of them are because Beamer makes the pause command into different slides. But second, I brought more slides than I intend to go over because I wasn't 100% sure what the audience of the talk might be. I tried to prepare a sort of colloquium talk, but if all the people here know what a topological phase of matter is, then I can skip ahead and get into some of the more technical details later. So feel free to express your opinions to me about this in chat or by unmuting and letting me know or otherwise. But we'll.
Yes, Arun. It would be nice to maybe clarify conceptual question along the way. And
okay.
Both the experts and also the new people will be familiar with, for example, like what exactly is a symmetry you're talking about. Maybe it's ambiguous word for many things. Anyways, I said along the way. I was just.
Okay. No, I'm just trying to. Okay. Sorry. Yeah. Yeah. Well. Okay. We can talk about it when it comes up. Sounds good. Okay. So in that case, and of course, whenever people have questions, please let me know. I have chat open on my other monitor, but if I miss something, or if you want to ask audibly, then feel free to unmute and let me know. So, okay, so I think I more or less said this outline that we'd like to classify topological phases of matter. So I'm going to say a little bit about what that is, not in complete detail, and then. So this question turns out to be difficult for several different reasons. And some of those reasons are hard, open mathematical questions. But even if we had, even if a paper were posted on arXiv tonight that solved those questions conclusively, there would still be important difficulties. And so we're going to restrict to something where the category theory is less intense. And so in this case, you end up, you only have to care about stable homotopy theory, which is nice because algebraic topologists have been developing tools to attack problems in stable homotopy theory for over half a century. So parts 1, 2, and 3 are a relatively standard story. And then what's more interesting is, okay, well, how do we deal with symmetries which act on space in this matter? And so that's hopefully where I'll get into some of the newer stuff. But first, just topological phases of matter. So the story began in condensed matter physics, where people studied these certain systems and are going to be vague, and they noticed these unusual topological properties. So I'm being vague about the kinds of systems because I don't have a clear idea of, okay, in these kinds these kinds of materials you get this behavior, and these kinds you clearly don't. But in the examples that I've seen, in for example, in a class or whatever, these looked something like, okay, you have this particular alloy of metals and you cool it down to a certain temperature, and then maybe you do, you hit it with a magnetic field of a certain strength, and then it displays these unusual properties. And so the way these properties come about is, well, okay, it's a metal, has electrons that move around a lot, and they get entangled in interesting ways. And so they behave in ways that I think a priori people weren't expecting. So, I said entanglement, this is a very quantum phenomenon. And so one manifestation of this is something which sounds like nonsense. You get particles in this, which are neither bosons nor fermions. And so these are called anions. I'm going to tell you about abelian anions, which are sort of nicer behaved ones, partly because it's a little easier to explain, partly because I think the track record of observing these as opposed to theoretically predicting them is on firmer ground in the abelian case. So, okay, well, what does it mean for something to be a boson or fermion? You have some particular kind of particle, and you put them near each other, and then you move one around the other. So, you have some wave function describing the system, and if you swap them, if you swap these two particles, well, ultimately, because swapping twice can be isotoped into, like, you can sort of untangle swap in 4 dimensions. That ultimately implies that what you get has to square to 0, or has to square to 1. So your two options are 1 and -1. And so we call something a boson if you multiply by 1, and you call something a fermion if you multiply by -1. And so this is sort of the fundamental, like, either or in particle physics, I think. So in lower dimensional systems, you can't untangle swap. And this is not a problem because we live in 4-dimensional spacetime. But in some of these topological phases of matter, well, they behave as if they are low-dimensional systems. And so you have these things which are not particles, but which behave an awful they behave a lot like particles. It's convenient to pretend that these things, these like localized excitations, that they are particles. If you sort of pretend that works, then you get a that's a useful abstraction for dealing with these systems. You can fuse particles, you can say where they are, etc. And so these things can be called quasi-particles, or they can be called anions. And so the key fact is that when you braid two of them, you move one around the other, then the wave function. So for abelian anions, you multiply the wave function by a phase, but that phase is not just 1 or -1. So I want to make clear that this is a weird thing. We know what the particles are, and what we're doing is in these things we have this thing with we're not introducing new particles. We're just getting stuff that behaves as if it feels like you put a bunch of electrons together and got something which very clearly is not an electron. So this is like in research, when you say, oh, this is weird, what do? You look into it. And so we'd like to have a good, first a good theoretical physics model of it, and then a rigorous mathematical model. And so the theoretical physics models are there, and the math is still, there's still some hard questions. So these things, these things arose with, in, for example, metal alloys or crystals. And so typically atoms are in some sort of lattice, and often this lattice has a high amount of symmetry. You can translation or crystallographic or whatever. And so often people formalize these in terms of what are called lattice-hamiltonian systems. So it's sort of, it's like if maybe you've seen quantum mechanics or quantum field theory things where you have a Hamiltonian, you have a Hilbert space, but everything is made discrete. So specifically, you have the medium that you're putting the material on, or you could think of it as space if you're in some sort of quantum field theory system, and you're going to discretize it. So maybe you say, okay, well, I want a sphere. Well, okay, a sphere is too like wibbly wobbly. I'm going to pretend that I'm on like a cube. Or maybe in 3-dimensional space, I say, okay, I replace space with the cubic lattice. Wait, was there a question?
I think not.
Okay.
I suppose because it's not the auto mute when people join, so that's why.
Oh, I see. Okay. Cool. Well, if people have questions, you can always feel free to ask. So you have this combinatorial structure, and the idea is to build this quantum mechanics like thing using only the combinatorial data. So you forget that you had any smoothness whatever. You just have a bunch of edges and vertices and faces, and you use that to build a Hilbert space of states. So some complex vector space, which because of the combinatorial nature, these things tend to be finite dimensional. And for the corner of math that I come from, this is like very reassuring. It makes things easier. So you also define a self-adjoint operator called the Hamiltonian. And so you can think of the Hamiltonian as telling you how, it could eigenstates of the Hamiltonian are, tell you energy levels, states with particular energy. Exponentiating the Hamiltonian maybe tells you how time evolution goes. And, this is also vague, but both of these things should be local. So physics in general should be local in quantum field theory, where you don't depend on things that are happening arbitrarily far away. So what that actually means here is using the triangulation, you can define some notion of graph distance. Okay, two simplices. How far are they away from each other? What's the shortest path through other simplices? And what you say is you pick a cutoff, some number n, and you say that the Hamiltonian, the Hilbert space is a tensor product of vector spaces which are built from combinatorial data that's not just only depending on the combinatorial structure, but only depending on the combinatorial structure, distance at most n away from a specific point. And you tensor those together overall vertices or edges or whatever. And similarly,
I have a question. Since we're maybe trying to be mathematically rigorous here, I think for infinite lattice, which is what we care about with topological phases, the Hilbert space is not actually defined, right?
So that's a good question. The way that I've grown up thinking about this is that we put these things on compact manifolds, and if there's a boundary, you choose boundary data. So, for example, maybe that means enforcing periodic boundary conditions. So you're on a torus, and then the Hilbert space is okay. I'm not really used to thinking about an infinite dimension, an infinite lattice. You have to do some sort of like you have to sort of cut off your function or provide a decay condition, right?
Well, it's just that when we classify topological phases, you always have to classify from in the thermodynamic limit, because in finite size systems, kind of everything is in the same phase as everything else.
Is this? Well, okay, question. I want to make sure I understand what you're saying by this. So let's say I put Kitaev's Torah code on a surface of genus G, and I triangulate it, and then I consider the trivial phase on the same surface. And so to my eyes, these things are different because one of them has a ground state degeneracy and the other doesn't. And you're saying something different than that, and I want to make sure I understand.
Actually, the ground state degeneracy for a generic Hamiltonian, the Kitaev Torah code is very special, but a generic Hamiltonian, the ground state degeneracy would be split by an amount that goes exponentially to 0 with the system size. So it's not actually degenerate for a finite system.
I see. Huh.
It may not be the important point for what you want to talk about today, but I'm just wondering.
No, this is okay. This is a good thing I should learn more about. Thank you for asking. But so for me, because these things are foreshadowing a little bit, these things are tied to topological field theory for me. And mathematicians, or at least this mathematician, only know how to define topological field theories on compact manifolds.
Right.
And so for that reason, I think, okay, a topological phase is sort of like a topological field theory. At low energy, it should be one. And so I want to say, okay, well, let me put it on the same things.
Maybe a question to rephrase. The central issue here is that when a mathematician can deal with infinite dimensional Hilbert space system or just finite dimensional Hilbert space.
Well, I thought the problem was an earlier one, which is like, okay, you have the infinite square lattice. How do you define the Hilbert space of, say, the Torah code on that infinite? That's where these like analysis problems come in, right? Like I want to tensor together infinitely many copies of C squared, or of infinitely many qubits, I guess. And what does that make sense as a Hilbert space? Is that what your original question was getting at?
Yeah, that was the question. Yeah.
Okay. Yeah, that's a great question.
If I could
jump
in. In this particular case, I think, so, I know that the, infinite tensor products of Hilbert spaces can get very sophisticated, and I don't know a lot about them. But in cases like this, I think there's often a standard choice of tensor product, which is the L2 functions on, like the space of L2 functions on the lattice.
I see. Okay, that makes sense.
So I know in particular that, so if you're dealing with like a tight binding model of an electron hopping around on a chain of atoms, I think that Hilbert space, the space of L2 functions on the integers, is the standard one. And then you can.
I think that's for non-interacting problems, but here we want to talk about interacting, so I think it's more difficult.
No, I mean, a tight binding model is interacting, right? The fact that the electron can hop from one site to another means.
Sorry, I mean non-interacting in the sense that.
Is this like quadratic terms in the Hamiltonian deal?
Yeah, but it's tight binding model is only quadratic terms in the.
Okay. Huh.
Interesting. Okay, so this is something I would like to know. I would like to know more about. Maybe I can ask you more about this at some point, because this is related to something I've wanted to understand.
But let me just make sure. Yeah. Why is this important? Is it this important to your development later?
No, not for today. Yeah, so maybe we should talk about it after.
We shouldn't talk about this now.
Yeah. Okay. Let's. Yeah. So I'm gonna continue then. So this part of the talk is the less mathematically rigorous part, because not all of these things have been precisely mathematically defined yet, as you just saw. So another thing I would like to make precise is that, but we don't know how yet, is that the Hamiltonian has to have a gap between its smallest and next smallest eigenvalues. And you're thinking, okay, that is a precise thing, spectral gap, it's a mathematical term. But when it comes to like taking continuum limits, if this is a useful phrase, that's something that, like, how does the gap behave under that is something that is, I think, is still a question. But we would like we'd like there to be this gap between the smallest and next smallest eigenvalues. And this is part of wanting to get something topological out. Otherwise, it doesn't behave as well. And another thing, and this is one of these weird things, which we understand it in examples, but the general theory, who knows? So the space of ground states, so that the eigenspace for the smallest eigenvalue of the Hamiltonian, in these examples, it depends only on the topology, but it doesn't know anything about the triangulation. And so there's physics reasons to expect something like this, but this can be very subtle, where you write down a Hamiltonian that looks like it should be for a topological phase, and instead you get these fracton systems which know a lot about the triangulation. So I'm going to leave this as a mystery that I don't know how to even begin to make progress on. But these are things that we would like our examples to have. And then, okay, so I've talked about, I've said both system and phase. And for a system, I mean some actual, okay, I have a lattice Hamiltonian, but phases are kind of equivalence classes of Hamiltonians under smooth deformations that preserve the gap. And so, okay, I'll say something about that later, that there's sort of like a space of these. We remove the gapless ones, and then we take the set of connected components, and that should be the classification of phases. I'm going to be vague about symmetries as well, but you can imagine you have a Hamiltonian on a lattice, and this can have a large amount of symmetry. So for example, maybe you can pick up the lattice, rotate it 90 degrees, and put it back down. So symmetries are important for any question, and I'll say a little bit about that. First, when the classification question, we're going to fix the dimension. So different dimensions have different flavors of classification. It gets more categorical as the dimension increases. And second, okay, this is what I was saying, is that we want to make explicit which kind of symmetries we care about. So when I say I'm classifying, two-dimensional phases, do I care about equivalence classes where I make sure that like everything preserves time reversal symmetry, or am I allowed to break time reversal symmetry? There's also fermion parity, there's additional symmetries. And, these things began in lattices typically with a high amount of crystallographic symmetry. And so in this case, people care about systems with that respect that symmetry. And they care about equivalence classes of phases where that symmetry is preserved. And so this acts on space. And this is going to be important in the second half of the talk. And so, okay, I said this, that we got to fix the kinds of symmetries we're talking about in order to ask a well-defined classification question.
I think there's one point, maybe there is some subtle part. One slide earlier, you mentioned that if two gap faces, topological faces can connect to each other without closing the gap. You are saying that they are the same phase. It will not be true if those two faces are non-invertible topological phase, which is non-invertible TQFT. You can still can have a non-trivial gap, domain wall, or interface between the two phases, and
but then they're not equivalent.
Right, they are not equivalent. They could be, but for invertible one,
I think the definition here means you can deform them as a function of parameter, not as a function of space. So you don't talk about domain walls.
Yes, that is what I was trying to get in here. Is like, yeah, okay, I see what you're saying. But
I saw that I shouldn't quote people, but actually there's a same question asked by Witten during the String 2021 meeting last week.
Oh, I clicked on the strings last week.
Yeah, that question was that is that the interface between two gap TQFT is related to a way to thinking about deform the Hamiltonian system along the time direction? I think the answer Witten's think is yes. So I suppose you can still think the gap interface between two non-invertible TQFT, but also topological phases, in a sense, if they can relate by a gap interface, they should be able to deform to each other also along time direction for some Hamiltonian system. Is this statement yes or no? I think we can say yes, and Zohar Komodowski at that time also say yes.
I trust both of them very much.
I suppose related. I don't know whether Shukang has commented.
Well, even if you can, if two topological phases have gap boundary, you can definitely deform. You can deform one to another by creating, one phase inside another and then grow it to the entire system. But that's equivalent to some circuit or some transformation that's some circuit that is as deep as the system size, which is not what we usually allow when we define equivalence of phases.
Oh, you want your circuit? This is like a finite depth circuit thing?
I think so, right?
Okay. Oh, okay, that makes sense.
Yeah, that's a good point. But just from this statement, it doesn't rule how the two phases can still be related in the sense of not closing the gap, but not possibly require using this not a finite depth, or using this large range of the unitary transformation that the man talked about. Yeah. Anyway, but conceptually, since we are here, I just clarify one thing. It looks to me probably the way to think about without closing a gap or changing the TQFT might be that you maintain the first eigenvalue and the lowest, the zero energy modes gap, but you somehow bring down some high energy states in some way and mix with the non-zero eigenvalue states, and you can change the system. That's what I have in my first impression when I talk about when I heard from Witten make that comment. I saw that that's possible because of this reason. But anyway, I don't want to derail the talk. I think that there's just some fine point about this, the last bullet point that you mentioned. Actually, yeah.
This is good to know. Thank you. So I'll tell you what I know from the TQFT point of view, and then continue. Which is, so the perspective in TQFT is that you have two top, like the analog of a domain wall is you have two TFT. Well, it's a domain wall, and so typically a TFT is specified by some kind of algebra. Maybe it's like a monoidal category, so it's categorified, and then you have two algebras, and you have a bimodule between them. So in dimension 2+1, it's a spherical fusion category which has a fusion product. You fuse the anions, and there's a notion of a bimodule category for that. And so you can have, what Juven said is related to the fact that you can have bimodules for fusion categories C and D, where C is not equivalent to D. that's fine. Just like you can do this for ordinary commutative algebras, or non-commutative algebras rather. And but that gives you data that sort of goes all the way up to level n-1. So in this case, 1. And if you ask for your domain wall to extend all the way up to level n, sort of the top level, then I think you get an equivalence of theories. So full disclaimer, this is, I have understood this partly, but not fully. And especially, that last statement is something that Dan told me that I haven't worked through yet. But that might be related where I'm thinking of this as like, all the way up to level n, and someone else is thinking of it as up to level n-1. And that's why we get different answers, but I would have to sit down and think about that. So thank you for bringing up this point though. This is great.
Keep going.
Yeah. Okay, so we're going to fix the symmetries we're talking about, and sometimes there's spatial symmetries, which is going to be important. So the classification question, we'd like to say, okay, there's a space of lattice Hamiltonians and a locus inside that which is gapless, and then the set of phases should be the set of connected components of this. You sort of have you have nice things, you remove the degenerate locus, and you continue. So making this precise seems to be very difficult. And so what we're going to, my whole method of approaching these things is to sort of work around this rather than directly attack this idea, simply because it seems really hard. And heuristics, I've sort of showed my hand that this is really about topological field theory, and classifying topological field theory grows in complexity as the dimension increases. And this has to do with higher category theory. And so even if you sort of take for granted that this works, then there's going to be these higher categorical difficulties. And so we need, in order to make any progress on this, we need good heuristics or indirect ways to get at this. And so even if you want to attack the problem directly, you got to know where you're going. And so that's where these heuristics are helpful. And they still lead to interesting math questions. And also, we should start with an easier subclass of topological phases. So I think it's required when you give a talk on topological phases to show a diagram like this one. So this is not a topological phase. This is water. And what it is, the point is, it's a model, a simplified model for what I mentioned. There's a space of Hamiltonians, say, or a space of parameters. And in this case, you've got the temperature and the pressure, and you could add more things if you want, more parameters if you want. And you've got these critical phase transitions, these black lines. And so what you do is we're going to ignore this part over here where the temperature is high enough that liquid and gas are not well defined. So let's cut off before, say, 450 Kelvin. So what you have a space which is connected, but when you remove the degenerate locus, which corresponds to gapped phases, you get 3 different phases: solid, liquid, and gas. So this is the kind of picture that I have in my head when I'm thinking about that sort of space of Hamiltonians, except it's going to be more complicated because there's more than 3 things.
Should I, or if I can interrupt for a quick question?
Yeah.
Should I imagine that the degenerate locus is kind of where, there's if I move a little above the liquid gas transition, then liquid is the ground state. And if I move a little bit below, then gas states are the ground states. And at the degeneracy point, at the transition point, they switch. And that's why there's a degeneracy? Or is it
yes, I think that's right. Oh, sorry.
Okay.
Yes. So I think what you these you can think of these gapless phases as, okay, you have a phase transition between this one phase and this other phase. And the examples that I've looked at, that is what happens, where you have a space of parameters, and at 0 it's degenerate, say, and at positive you're in this phase, say trivial, and negative you're in this other one, which is non-trivial. Mm-hmm. So yeah, that is what's happening.
Thank you.
So just one thing. So what you're describing is what we would call a first order phase transition.
First order.
There's also continuous phase transitions where the system becomes gapless, but not because one ground state is just crossing over the other ground state, but because the correlation length diverges. Anyway, that's just a physics point.
This is good to know. Thank you. Are there more questions before I go on? All right. So what we're going to look at is what's called invertible phases. And so there's this operation you can do to topological phases. And again, I'm sorry again for being kind of vague, but we don't have precise mathematical definitions for this yet. So what you can do is you can imagine. So as a model, I often think about, okay, I have quantum mechanics, I have two different quantum mechanical systems, and I sort of put them far apart, spatially. And maybe they're part of the same system, but they don't talk to each other at all. So this is not quite the same thing. We're putting two systems on the same medium, the same space, but we're saying that they don't interact at all. And so this is something sort of like a tensor product. In fact, you literally tensor product the Hilbert spaces, and you tensor product the Hamiltonians, H1 tensor 1 plus 1 tensor H2. And so what we're going to do is we're going to say, I care about things which are invertible under this. So this is a severe restriction. What are the invertible vector spaces under tensor product? They have to be one-dimensional so that you can tensor with something and get back to the complex numbers. So invertible phases, just terminology, I like to call them invertible phases for no particular reason. You will also see the notation SRE for short range entangled, or SPT, symmetry-protected topological. These should all mean the same thing. And so what invertible means, sorry, I should have said this a little sooner, is that you take your phase, you have some other phase such that when you stack them together, you can obtain the trivial phase. So when you stack them together, you don't literally get the trivial Hamiltonian. You have some stuff, but you can, under these gap preserving deformations, you get back to the trivial Hamiltonian with no interesting physics. And so, like I mentioned, this is quite a severe restriction, but it's sort of a good place to get started, a good foothold, because the classification is more tractable. So instead of like an n category, what we have is in any dimension that you fixed and fixing what symmetries you care about, you get an abelian group. And so condensed matter physicists have spent a lot of time computing these groups in the last maybe 10, 12 years. And you get out these interesting answers, and cool math comes into the question. So for the rest of this talk, I'm only going to care about invertible phases. So Kitaev has been a big proponent of the fact that the mathematics that you should use to classify invertible phases is stable homotopy theory. So specifically, if you fix the symmetry type but allow the dimension to vary, then the space of invertible phases should actually be a spectrum. So I'll say what a spectrum is in the sense of homotopy theory. If you have not heard of the notion of a spectrum and you think this is related to the spectrum of a Hamiltonian, I have some bad news for you. And this notational convention has been confusing people for at least 50 years. So sorry about that. But the point is, a spectrum is sort of like a topological space. I'll say what the differences are, or some of the differences. And so you can take homotopy groups of spectra. And in particular, the dth homotopy group should tell you what the group of d-dimensional invertible phases is. So I'm going to give two justifications for this idea. One is more directly physical. And I think I've seen arguments like this in a couple different places, but the version I used is directly from a paper of Davide Gaiotto and Theo Johnson-Fried. And another is more mathematical, which I learned from Dan Freed in his work with Mike Hopkins. But first, I should probably say what a spectrum is. So spectra are built to study what are called stable phenomena in algebraic topology. So this means something vague, but less, maybe a little less vague, which is you do some operation to some topological space that you care about, and you do it enough times and the answer stops changing. And that's what I mean by stability. So the key example is you can do something called the suspension of a space. And so what the suspension is let's say X has a base point. So I picked a particular point in that space, and S1 has a base point, the point 1 in the unit complex numbers. And so I want to take the product with a circle in a base point preserving way. So if I take the product of S1 cross X, that has too many base points. The base point of S1 cross any point and any point cross the base point of X. So what I'm going to do is I'm going to say all of those points are just one point. I crush them into a single point, and that's the suspension. So suspension, it's a fact in Hatcher that you sort of, you prove in your first course in algebraic topology, that suspension induces an isomorphism on homology and cohomology groups. Sorry, you have to shift it, I should say. But the essential data in the cohomology groups is not changed. It's just moved around. Moreover, homotopy groups, again with a shift, stabilize if you suspend enough time. So suspension is not an isomorphism on homotopy groups, but if you do it enough times, then homotopy groups stabilize. So this is some So the point is that you could imagine suspending a space enough times and getting stable information with regards to cohomology and with regards to homotopy. And these are the two fundamental invariants in algebraic topology. So so we'd like to model that. We'd like to study the stable behavior. So we'd like to model that stable behavior with objects which, well, have that built in. So spectra, from this perspective, are objects which model stabilized topological spaces. And so to clarify, a stabilized topological space with respect to suspension gives you a spectrum, but not all spectra arise in this way. So another perspective, there are many different ways to think about spectra, and I'm not going to tell you about all of them because that would put you all to sleep. So one thing you could say is that, oh, there should be a close quote here. Sorry, homotopy classes of maps to a spectrum ought to be a generalized cohomology theory, and so this has something to do with the fact that that cohomology is already stable, that suspension just produces a shift isomorphism. And so maybe things that behave like cohomology, but maybe aren't quite the same thing as it, which are called generalized cohomology theories, maybe these things should be, maybe spectra should be objects which represent them, meaning that maps to a spectrum give you generalized cohomology. And maybe those two things should be the same thing. And this is the sense in which I care the most about spectra right now. So another perspective is that spectra are sort of like chain complexes of abelian groups. And this is sort of a categorical framework, that there is a derived category of chain complexes of abelian groups, and it has some very nice properties. And so what if we did something like that, but sort of built out of topological spaces, or maybe built out of generalized cohomology theories? And so if you follow your nose, what you get to is spectra. Although when I say that, a large amount of hard work by many people went into that. So these three very different perspectives are different reasons that mathematicians care about spectra. But actually, okay, what is a spectrum? So, before I go on, I should say this perspective, chain complexes of abelian groups, is what's going to pop up later in this talk. But the precise definition of a spectrum, we want to sort of, to stabilize with respect to suspension, we want to be able to undo suspension. So the definition, okay, there are different definitions which give you equivalent theories, but I'm just going to pick one. So we want data of homotopy equivalences so we want a space for each natural number, and we want a homotopy equivalence from one space to the loop space of the next space. So omega denotes the space of maps from S1 into xi plus 1, and I want the base point to go to the base point. So there's an adjunction between loops and suspension. So it's equivalent to ask for maps from the suspension of one to the other. And when I say equivalent, you're not getting literally the same data, but we care about homotopy theory, and these two desiderata give you the same homotopy theory. I can say more about that later, but that's a mathematical point that I think is distracting from the physics. So this data is saying something like, you can use this to define the inverse to a suspension. So you can suspend a spectrum by sort of shifting everything one way. Or sorry, you're sort of shifting everything to the left. You're losing x0, and you're saying, okay, start with sigma x0, which is sort of like x1. But you can also invert suspension by shifting everything to the right. And so it turns out, okay, that the suspension functor is just invertible. And so what that means is that when you suspend, you can't lose any information. And so that's the sense in which spectra are stable with respect to suspension. And so phenomena which are stable with respect to suspension, such as homotopy groups eventually, or cohomology, can be made sense of in the world of spectra. Let me pause for questions. I'm done with the sort of the math part of here's what the definitions are, and now we're going to get back to some physics. So let me just check that there's nothing to chat about. Okay. So there's this argument of Davide Gaiotto and Theo Johnson-Fried, which says that invertible phases are a spectrum. But before that, here's some crazy big mathematical object that the homotopy theorists have been working in a corner for a bunch of years. Why should we care that it has this structure? So stability, the definition of spectrum is more complicated than that of a space, but it simplifies things. So this is the common trade-off in algebraic topology, the conservation of effort. And so ultimately, it turns out that homotopy groups behave like a homology theory for spectra. And this is a magical thing, because homotopy groups are powerful but hard to calculate for spaces, and homology is easier to calculate but provides less information. And again, conservation of effort and trade-offs. So in spectra, you have a sort of best of both worlds, that homotopy becomes homology, well, generalized homology, and that makes it nicer. Now, homotopy groups of spectra can still be very difficult. For the spheres, for the sphere spectrum, the sort of the basic object, we'll never know all of them, but it's still better. And so if you care about homotopy groups if you have an object and you want to know its homotopy groups, say the space of phases, it's helpful to know that it's a spectrum because, hey, Aaron, what's your question?
Just real quickly, what does a spectrum go down infinitely, up infinitely, or both?
It can be both. Great question.
Okay.
So weirdly, so spaces have homotopy groups indexed by the natural numbers, and spectra have homotopy groups indexed by the integers. And this is weird because, like, what's a negative three-dimensional sphere, right? So what you think of it is you shift up a bunch because you can do that. Then you take a positive dimensional homotopy group, which actually makes sense, and then you shift back down.
Okay. So should I think? Yeah. I guess what the specific thing that confused me was usually I think of sort of looping as making something more complicated. So it's weird to me that, like, you have an isomorphism between something and, like, the loops of the next thing up.
Yes.
So should I sort of be thinking that, like, how do I say, the space is getting more complicated as you go down?
I think that's a useful piece of intuition. So once you get to spectra, then loops are an equivalence. Like, so suspending is sort of shifting in one direction, and loops is just shifting in the other direction. And so it's like, so homotopically, if you take the loops, the base loop space of something, it's more complicated, right? So like the the loops of the three sphere has cohomology in arbitrarily high degrees. But if this is this like stabilization phenomena that if you do this enough times, then you sort of maybe that's okay. Maybe I don't want to say something wrong, but the way that I think about it is that, okay, you in the unstable range, you do some stuff and it's complicated and not as easy to understand. But once you do this enough times, then you've passed into the stable range and things behave much better. And so it's true that your space is like, horribly infinite dimensional. But as far as homotopy theory goes, you've said, okay, I have this space. It's big because it's a loop space, but its homotopy theory is something that I understand. So I don't care how big it is.
I see. So you're saying things are nice on the negative part of the spectrum because things have been looped a lot of times and eventually they stabilize, but things can get sort of arbitrarily nasty in the positive part.
Not quite. So I guess I think about it as like, so the different spaces, the negative and positive parts, are sort of not the most intrinsic, because I could, for example, suspend and then loop and suspend and then loop, and therefore make things much more complicated. I guess I think of the whole spectrum as, okay, there are some spaces and, maybe they're kind of weird, but as far as the things that I care about, I can't tell. I don't care. I take cohomology and, it's like the cohomology of S1 versus the cohomology of some infinite dimensional space that's homotopy equivalent to S1. The difference is not important to me. And something similar is happening here where, the process of actually building a spectrum that you care about might involve some very complicated data. But once you have that, you can sort of you can sort of close the black box and just work with your object, and everything is fine. It's sort of like, okay, here's an analogy. So spectra are like chain complexes. The singular chain complex on a space is huge. It's nasty. It's infinite dimensional. We don't know how to calculate with it, right? But it's equivalent if you have like a triangulation, it's equivalent to a much smaller CW or chain complex that's like better behaved. It's finite dimensional in every degree. We know how to compute its homology. And in homotopy theory, we don't care about the difference between those two. So, the fact if I started with singular chains and it's just this like terrible infinite dimensional thing, well, who cares? It behaves fine. And so I think the intuition for you to how to think about chain complexes that are infinite dimensional should be helpful. Like, you should carry that analogy here.
Yeah, maybe I should have asked for now. I want to continue this after in the question,
sure.
But maybe I should have asked for now a simpler question, which is a topological space, an ordinary topological space, an example of a spectrum in some canonical or almost canonical way?
sort of. So from a topological space, you can build a spectrum called the suspension spectrum. And so I said that you could ask for maps like this. So what you do is you say xi is the ith suspension of x. And then, okay, this map, you say, okay, the suspension of the ith suspension is the I plus first suspension. So you say this map is the identity. So that's how you go from spaces to spectra.
Okay. So in this case, the spaces look like they're getting more complicated as the numbers go up. Can I also build like a loop spectrum where it goes the opposite direction? Where like, x0 is your original space, x, the
so
next
the trick is that you're indexed by the natural numbers, so you can't quite do that.
Oh, sorry, that's what okay, thank you. Okay.
Yeah. Oh, sorry for the confusion. Okay, wait, so this addresses your question?
Yes, this addresses the question about.
Okay, cool. I'm gonna go on then.
Thank you.
But by all means, please ask more questions when you or anyone has them. So so as I was saying, that spectra are it's nice to have a spectrum because that means that things fall apart into nicer invariants. Like for example, Postnikov theory is easier if that's a useful word. And also, the way I like to think about this is that a bunch of algebraic topologists have been sitting in their offices for 60 years, 61 years, carefully sharpening their knives and using them on their own very difficult problems. And now we have physics problems, which are not always as difficult. And so, we have these knives, we can cut into these problems. So first, okay, let's talk about this argument that I learned from Gaido and Johnson-Fried's paper. It's similar to stuff that I've seen in work of Charles Chiong and also to Kitaev's ideas. So let's ignore the problem I said that making a space of gaphamiltonians is hard. Let's suppose that someone has done. Because we do expect that the space to exist, just that there's mathematical problems in making it rigorous. So there's a space P for P for phase of invertible gapped phases with the symmetry type fixed. So we want to describe a map on loops of Pn to Pn minus 1. So a point in the loop space is a path in the space of topological phases, which starts and ends at the trivial phase. So we're going to consider an n-dimensional system on R, which has coordinate t, and Rn minus 1, which, okay, we have our loop. And so we say start at the trivial phase, when t is negative and not like big, we're in the trivial phase. And then as t gets closer and closer to 0, we start walking around the loop. And now we're doing something that could be interesting. And we only do that for a short time. And once t is a little bit bigger than 0, then we're back in the trivial phase. We just keep extending out to infinity. So what does this mean precisely? This is related to, I think Dominic asked this question earlier. How do we put this on an infinite lattice? And I'm going to skate over this. This is a heuristic argument. And so now you zoom out and you can say, well, this is mostly trivial over here. What's really going on? All the physics is just contained in this n-1 dimensional subspace. And so once we understand what Pn and Pn minus 1 are, this ought to be precise, but we don't have that yet. So Gaido and Johnson-Fried also, they also give arguments for why this map should be a homotopy equivalence. That's not strictly necessary to define a spectrum, so I'm gonna skip it for now, although it is a nice thing to have. So the next thing I'm gonna say is this low energy approach. Okay, so how much time do I have? It's now 8:50, and I'd like to say a little more, but I also, running over time is a bad thing. I can definitely finish by 9.
We're happy to hear as much as you are willing to say.
Okay.
I also agree. I think you should, just don't rush. Take your time.
Okay, thanks. What I'm going to do is I'm going to try and make sure that, I'm sure some people have to leave at 10 because time zones, and so I'm going to try and get to something like a nice satisfying conclusion, and then if maybe continue afterwards if there are people who are still around. Okay, so hopefully that works for everyone. And I'm sorry that I'm going to go a little over time. So this approach I'm going to spend more time on because it's the one that in part because the one I understand better, and in part because it's closer to my own heart in terms of the kinds of algebraic topology I like. It has to do with borderism specifically. So this perspective, the low energy classification of invertible phases or any phases, is taken up by Dan Freed and Mike Hopkins. And again, you have to go through some physics heuristics, but then you get to mathematical questions that I know how to wrangle. at least some of them. So, we'd like to take some sort of low energy cutoff of a lattice Hamiltonian system. So maybe you say, okay, well, all these, I'm just going to throw out my eigenstates with eigenvalues that aren't just the smallest one. And defining this precisely is hard. We don't know how to do it. But it should be true that topological phases are well approximated by topological field theories, which are unitary, because we started with unitary physics. And invertible phases should be well approximated by invertible field theories. And so I said reflection positive here, which is saying that I'd like my physics to be unitary. Invertible is relating to the fact that we started with invertible phases. And we know how to classify these mathematically. So you take one physics leap, and then you get to a mathematical question. So we have this mathematical model due to Atiyah and Siegel, and then many people after that have been building on it. For example, extended field theory, or how do you incorporate reflection positivity? That's Theo Johnson-Fried has some stuff, as do Freed-Hopkins. So a topological field theory is formalized as a symmetric monoidal functor from a category of borderisms to the category of complex vector spaces. So in my experience, saying this to physicists usually produces some unhappiness. So let me say concretely what this means. So to every closed end manifold, so again, I care about finite volume things. And this is important. We're going to assign a vector space of states. So we should think of this as the Hilbert space of states. In topological field theory, somehow the Hilbert structure is not necessary or goes away sometimes, and we're not going to worry about that right now. And just like in quantum mechanics, if you have these two things which are separated and can't interact with each other, you take a tensor product. And so that means that disjoint unions of closed manifolds get sent to tensor products of vector spaces. So this is under the hood, the word symmetric monoidal is doing a lot of work, but this is what it means heuristically. There's a little more that goes into it that is not important right now. So to every borderism, we're going to assign a time evolution map. So a borderism is it's a compact n+1 manifold X and an identification of its boundary with the sort of incoming component Y0 together with the outgoing component Y1. So you should think of X as a time evolution map from Y0 to Y1. And so this is called a borderism. If you've heard it called a cobordism, that's the same thing. So this is the part where physicists usually have some complaints, and I think that's fine. Topology change during time evolution is bizarre, right? Like, you're ripping a hole in space, and then you're putting it back together, and then you're tearing space in half. You're tearing me apart, Lisa. And so this is weird. So sometimes you're doing quantum gravity, and this is like more acceptable, but we're not doing quantum gravity today. So what the heck, Arun? And so what's actually going on, if this makes you uncomfortable, which I think is a very reasonable thing to do from a physics perspective, then you could think of this as a formal tool to use locality to compute partition functions. So the partition function of a topological field theory on a space-time manifold is local. Quantum field theory, it behaves locally. And so that means you should be able to chop your manifold into a sequence of borderisms and use that to compute the partition function. So in that case, it doesn't literally make sense to say, time evolution is changing the topology of space-time. But instead, what's going on is you have a manifold with boundary, you're choosing boundary conditions, and you're using that to determine a partition function. So hopefully that intuition is good if you aren't happy with topology change. So I'm happy with it because it's mathematics, and I came to this starting with the mathematics rather than the physics. But hopefully this motivation is helpful if this is from a physical point of view. So this is sort of related to the point that I made earlier, that classifying all topological field theories, just like classifying topological phases, is complicated. It's dramatically simplified by a conjecture of Baez and Dolan, which Lurie proves. There's also related work of Hopkins, Lurie, Ayala Francis, Chris Schomer-Priest, especially in low dimensions. And so the answer involves higher categories, which I personally think it's cool that this very abstract stuff has something to say about physical things, but it's just very tricky to make explicit. So as one example, I'd like to point you to this. There's this wonderful work of Chris Douglas, Chris Schomer-Priest, Noah Snyder, it's called dualizable tensor categories. And I think they've got some more papers on the way. And so they're saying, okay, we want to classify these in dimension 3. And it's just very complicated. It's elaborate. So, their hard work is indicative of how much harder it'll be in higher dimensions. And so there's a tensor product of topological field theories, and there's a notion of invertible phases. or sorry, invertible topological field theories, which is this, it's analogous to invertible topological field theories, where you say, okay, I want to be able to tensor with something else and get back to the trivial field.
Maybe can I ask a question?
Of course.
Just about the classification of TFT or TQFT in the mathematical sense, what kind of classification it is, for example, done by Lurie. In the sense, the question I want to ask is, physically, we know that suppose we use maybe, like group homology type of description, which is lowbrow compared to more general higher category. Then these are diagonal Witten topological gauge theory, and that has a data of for example, gauge group and some co-cycle twist. But sometimes we know that these data are just some way to enumerate some gauge theory or TQFT, but they could be redundant in the sense some of the data are repeated in the sense they actually collapse or they are actually the same TFT. So when you say the Lurie or other people try to classify TFT, do they have a scheme to really identify distinct TFT, or are they just enumerating as much as possible? Just based on the comment I make, that could be redundant label. Maybe there are several different labels, but they actually belong to the same physical theory.
Okay. This is a really great question. So the way that I think about it, I'm going to talk about first. I'm going to talk about quantum field theory just as an example. So n=4 super Yang-Mills has this famous S duality, right? Where you say, okay, I take this one group and I get this, this quantum field theory, and I take this other group, which is completely different. The Langland's dual of G in general is not the same as G, and I get this other quantum field theory a priori, and they're the same.
Right.
So if you wanted to classify quantum field theories, you would care about the quantum data, not the group that you started with, the Lagrangian. That's all sort of
Yes.
additional data. You say, okay, I want to classify I want the A model for G and the B model for G dual to be the same in my classification. And what's going on in Lurie's theorem is, he doesn't care about what the gauge group is. He doesn't care about, in some TFTs, you can make sense of like Lagrangians and like quantization, and he doesn't care about that. It's just saying, okay, a TFT is like the definition that I mentioned with the functor is just sort of the answer. It tells you how to compute things like local operators and state spaces and partition functions, but it doesn't tell you what's the Lagrangian, what's the gauge group, if there is one. We don't even know if all TFTs admit Dijkgraaf-Witten-like descriptions. They might. Sorry, I think that's true.
No. Should be no, but I'm just giving an example anyway.
Okay.
Yeah, that was just an example. I try to say,
So this is
these are like enumerate as much as possible. Are really, or is this really a classification scheme they propose?
It's okay. So Baez and Dolan proposed it, and Lurie proved it for topological field theories in the sense of a functor. So in that sense, it's a mathematical theorem, and it says here's what they all are. It's inexplicit, but so you're saying, okay, I want a homotopy fixed point for some object in an n category, but it's mathematically precise, and it's just there aren't any more as long as you care about fully extended theories, which are sort of the most physical ones.
But are there something more like, as you just say, it's more like a duality, maybe two different labels actually are the same, or actually more labels actually belong to the same theory or same phase? So
there are examples of that, but they're that's not addressed by Lurie's by this borderism hypothesis or these classifications. And some, like, you can come up with examples where you say, okay, well, I have these two topological field theories that a priori are different, but they're actually the same. But this classification just kind of ignores that. It's really
Isn't the theorem? I thought you said that the theorem is saying that we know that for a given set of data, and maybe you define some isomorphism class of that is in one-to-one correspondence with TQFTs. Like, isn't that the theorem that's proven?
Yes.
So then that seems like it's
exactly.
answering Juven's question, is that we know that doesn't occur here.
Yeah. Okay.
So there's also isomorphism. I thought that maybe a more familiar one, which Arun is going to talk about, is for the invertible TQFT. But you say also for the general TQFT, there's also some isomorphism class.
Yep.
That you can. I see.
Yeah.
Okay. So this will be the last question from this side. Is there some mathematical object you can say simply? What are the mathematical objects to classify?
So, okay, maybe this will be helpful. I'm going to say it in physics words, but I think that might be helpful. So if you have a topological field theory, you have any field theory, you have boundary conditions, right? And so in dimension n, this has maybe an n-1 or n or something categorical structure, which has to do with I think this has to do with the fact that you can sort of maybe you could compose boundary conditions in n different directions. So that's what I just said is super vague. But what the classification theorem, you could think of it as saying, okay, we have identified precisely what the possible boundary conditions are. If my TFT is valued in this particular target in symmetrical nodal n category, then so first of all, if you know the n category of boundary conditions, then you know your topological field theory up to isomorphism. And second, here are the possible boundary conditions that can occur. And so the condition is, first of all, that your category of boundary conditions is not too big. It's something called fully dualizable, which means something precise. And it's an analog of finite dimensionality for vector spaces. And second, there's some additional data that you have to say, okay, well, I care about oriented or spin or like pin minus or whatever. And you have to specify that data. But it's in the form of, there's sort of a group acting on the space of all of this stuff, and you're asking for a fixed point of that. Hopefully this is a useful answer to your question. We can talk more about it afterwards or at some other point.
Yeah.
I'm sorry that it's kind of vague.
At least I'm not the main point. Thanks. Anyway, thank you.
Can I ask one more question about this slide?
Mm-hmm.
So is it correct to say like the fully extended TQFTs are, at least from a physicist point of view, the same as TQFTs that can be constructed from state sum?
Ooh, good question. I would like that to be true. I think it's true from just like know it in my heart of hearts. I don't think there's a theorem that says that, but it's the kind of thing that, it better be true. Kevin Walker has some good ideas about this, in fact.
And is it expected that this is true? Or
yes, I think it is expected that that's true.
Okay, all right, thank you.
Yeah, thanks for asking. Okay, more questions before we restrict to invertible things. All right, so, n categories, cobordism hypothesis, whatever, very complicated. Invertible TFTs are an abelian group. And if you want to classify them, then invertibility buys you something really nice. You no longer have to care about higher categories in general. You have to care about what's called a higher abelian group. So this is like an NLab style terminology. And what I mean precisely by this is something like a Picard n groupoid or a Picard infinity groupoid. So, there's really higher category theory going on here, but at least from a heuristic point of view, it is in fact a lot simpler. So you have a commutative tensor product, and you threw out everything that doesn't have an inverse. So what you have is sort of like an abelian group, but like I said, higher. So if you follow the sort of the physics literature about higher symmetries, and like 2 groups to 3 groups or whatever, this is the same thing, except we're now imposing that things are abelian. And so this is how you get to spectra. There's a thing called the stable homotopy hypothesis, which was first proposed and then was proven recently by Moser, Ozornova, Paoli, Sarazola, Verdugo, that says that higher abelian groups are the same thing as a certain subcategory of spectra called the connective spectra. So this is another perspective on spectra, is that they're sort of like abelian groups, but maybe like incorporating this categorification. So I want to mention there's also important work of Gursky, Johnson, and Osorno, who did this in sort of the abelian 2 groups case. And then there's many other people who did the abelian the abelian 3 groups case was Gursky, Johnson, and Osorno. 2 groups case was done by many people. So the upshot of this slide is that invertibility buys you, through the stable homotopy hypothesis, it buys you a much simpler classification in terms of spectra. And we're going to get out pi0 of a spectrum, which is an abelian group. So what can I say about the homotopy type of the space of invertible TFTs? Is that, okay, we know that invertible phases should be classified by invertible TFTs. Maybe the word unitary should be there. And abstractly, we know that these things are a spectrum. So what Freed-Hopkins did is they said what the spectrum is for unitary invertible TFTs. And okay, I'm going to say what this notation means, but the point is they calculated what this is. And there's this is based on a couple of ansatzes about, for example, what properties do I want about a partition function? And one thing which, if not yet a theorem, it's certainly true, but it is technically a conjecture. But based on that, it's they get this mathematical answer for unitary invertible TFTs. So MTH is something called a Thom spectrum. Its homotopy groups are borderism groups of manifolds with H structures. So that's something that we understand pretty well, and maps into this thing IZ called IZ is called the Anderson dual of the sphere. And so this is saying I want to take borderism invariants rather than borderism groups. So an element of the homotopy group of MTH is a borderism group, so represented by things like manifolds. An element of this is something like the ARF invariant of a spin surface, or maybe the ARF Brown-Kerver invariant of a pin minus surface, or like the index of a spin 4 manifold. So borderism invariants. So a lot of this is part of a long story in algebraic topology, and related to physics, asking, okay, well, what can we say about the homotopy type of cobordism categories? So there's this work of Galatius, Madsen, Tillman, Weiss, which is sort of the kicking off point for why you should expect borderism to come in. There, Nguyen said, okay, well, GMTW found out as a space, we're going to find it out as a spectrum. Chris Schomerpries, who said, okay, let's put in higher categories. Gergely Sux and Soren Galatius, who incorporated equivariance. And so this is necessary to say things about unitarity. And then, many more.
Say what is an H structure?
Yes, sorry. Okay. So let's say that you have a group on a like ON or SON or whatever, and you have a manifold. So a manifold has transition functions, which are a priori they're valued in GLN, right? But actually, wait, Juven, did you want to say something?
Next, you answer first. I'll ask.
Okay, so an orientation is an example of an SON structure, because you say, okay, I have my transition functions, and a priori they could include like reflections. But let's say that I insist that they have determinant 1. So you can, up to some notion of, you choose a metric and you're an ON, but then you say, okay, I want my transition functions to be orientation preserving. And now my transition functions are actually an SON. So an H structure is saying that I have a group H with a map to ON, and I want my transition functions to be valued in H, not in ON. So orientations are SON, spin structures are spin N, and so on. Does that help answer your question?
So this allows you to, in particular, classify like spin TFTs if you say the right H and all of that. I see. Right. Thanks.
Yeah,
thank you for asking. Okay, Juven, what's up?
I just want to make sure. Shouldn't be MTH, the MTH should be Madsen-Tillman spectrum precisely, right?
Yes, sorry, that's right. So, okay, Juven makes an important point, which is that what is traditionally considered a Thom spectrum in mathematics is MH and is slightly different. And the MTH is called a Madsen-Tillman spectrum, MT. So here I was trying to avoid that point because, so a Madsen-Tillman spectrum is an example of a Thom spectrum, but I'm glad that you mentioned this because it's important to be precise. So thank you.
And I want to ask you why, so these are the map between two spectrum. One is a Madsen-Tillman Thom spectrum. The other is the suspension twice on this Anderson dual of a sphere,
Yep.
Anderson dual spectrum sphere. So why is the suspension is 2 here? Maybe you have a good understanding on that.
Awesome. Okay. So yeah, I can precisely answer that. So the way that Freed-Hopkins got here is they started with IC star, so the sort of the character dual or Pontryagin dual of the sphere, and then so that just tells you sort of isomorphism classes of things, and what they care about is deformation classes. So what that means is you say, okay, C star, instead of being a discrete abelian group, I'm going to put the topology on it, the usual complex numbers topology. And then it is true that as a topological group, C star is homotopy equivalent to the unit, to its unit circle, S1. And so S1, it turns out, is the classifying space of the integers. So it's not literally the suspension of the integers, but the upshot is that you've done something which stabilizes, which when you stabilize in the world of spectra, puts you in the suspension direction. That is not a super precise way of saying it. Let me So in other words, if you take the analog IC star, but you put the continuous topology on C star, what you get is not quite IZ. You get the suspension of IZ. And this has to do with the fact that you took the classifying space of Z to get S1. So that's one of the 2 degrees. The second one is easier. The second one is, am I in space dimension or space time dimension? And so if you said that I care about n-dimensional TFTs, where n is the space time dimension, this is just sigma IZ. But if your convention is to let n be the space dimension, then you get sigma 2. Did that help clear things up? Is there more things I can say about that?
Thanks. I'll think about this. Thank you.
Okay. So so let's say that you're so getting back to this sort of condensed matter question, one thing you could do is you can calculate homotopy groups of the spectrum that Freed-Hopkins found, and you can compare it with, physicists have spent a lot of time computing these groups of invertible phases, and so our mathematical model had better match up. So for example, in dimension 1 plus 1, you could consider invertible fermionic phases. So I'm not going to say precisely what that means, but it's an analog of requiring your TFT to have spin structure. And so we're going to have a time reversal symmetry, and we're going to say that it squares to 1. So these things are supposed to be classified by Z mod 8. And this was originally posited by, I think, Lukasz Witkowski and Alexei Kitaev, and then also Turner, Paulman, and Berg around the same time. And sure enough, the Freed-Hopkins classification says that we take the mapping spectrum. So in this case, the H should be pin minus, so an unoriented version of the spin group. And we take maps from MT pin minus into sigma 2 IZ, and we take pi 1 of that. So 1 is the space dimension. And sure enough, this is Z mod 8. So this is this is a fact about borderism groups that I think was first shown by either Anderson Brown Peterson or Vince Giambolvo, and then later again by Kirby Taylor. So okay, these Z mod 8s match. That's a good sign. But maybe it's a coincidence. So let's do it again. So 3 plus 1 dimensional invertible fermionic phases in which the time reversal symmetry mixes with fermion. So time reversal squares to the fermion number. So this is predictive of a Z mod 16 classification. So this is due to many people. Some of them include, so Kitaev had a talk on it, Witkowski, Chen Vishwanath, and then again, many, many more. So I know, and so, okay, well, we'd like to believe this from the mathematical perspective. And indeed, this is classified. So now this mixing tells you to get pin plus. And so, shoot, this 8 needs to be a 16. So sorry about that. This is a typo. This is the 4th pin plus borderism group, or the group of 4-dimensional pin plus borderism invariants, and that is indeed Z mod 16, not Z mod 8. Sorry, so this is generated by an eta invariant. So okay, so typos notwithstanding, we get the predictions match, and this is a good sign. So the last thing that I was going to talk about in this talk is what happens when you include spatial symmetries. And so I've got a couple more slides where I talk about that and just briefly what my work is. But since I'm already 15 minutes over time, maybe now's a good time to sort of pause, ask for questions, and therefore, if you have been looking for an excuse to leave, there's your excuse, and then I can go a little longer on the last part. Does that sound reasonable to people?
Yes.
Okay. So, I mean, thanks everyone for listening. Sorry that I went over time. Do people want to ask any questions here before I go on?
You haven't yet explained how to incorporate additional symmetries like unit symmetries yet, right?
Like what symmetries? Sorry.
Like just the internal symmetries.
So internal symmetries you would do by modifying the H structure. So for example, if you have just this auxiliary Z mod n symmetry that doesn't move space, it doesn't interact with fermion parity or whatever, your H, you would take the Madsen-Tillman spectrum of, say, pin minus times Z mod n. Does that help answer your question?
Yeah, sure, yeah.
Okay. Are there additional questions before I go on? Okay. So there's lots of different notions of symmetry that we could try and generalize. And I'm going to tell you about only one of them, which is symmetries which act on space. So, for example, you have a particular Hamiltonian on a square lattice, and you can pick it up, you can rotate it, you can put it back down, or you can reflect, or you can do inversion, or maybe you even have a tetrahedral symmetry on the cubic lattice in three-dimensional space, and you have a Hamiltonian system which is preserved by that. And so these come up in condensed matter applications because your material has these symmetries. Okay, I said this example. Oh, and I said that. So we'd like to incorporate spatial symmetries into the classification of invertible phases. And so there's a bunch of different approaches to this. And so one of them, I know there, Mike Hermele and his collaborators have this nice approach, this physics-based approach, which gives you some good information. And there's this general approach due to let's see, Thorngren and Elsa. So Elsa, who is here, and actually is Ryan might also be here. Anyways, so they have this nice perspective which says, okay, here's spatial symmetries are complicated. Here's how we can make sense of them in terms of something easier. I'll say a little more about that in a bit. But I'm going to try and do a different one because, so, if all you have is a hammer, everything looks like a nail. And my hammer is called algebraic topology. And I'm going to see if I can say things using algebraic topological tools. So I'd like to continue to use homotopy theory. And this is a problem because if you have a spatial symmetry, making sense of, okay, the low energy limit is a topological field theory gets less straightforward. So your spatial symmetry, I'd like everything to be fully local on space-time, or at least space. So but I have a symmetry which moves stuff. So I know that my symmetry takes this point and moves it over to that point. And I don't know how to localize that, like when I zoom in on a point. So that's not great. But what you can do, so Kitaev's argument that invertible phases form a spectrum or a homology theory, it generalizes to phases on a space with a G action. And so what you get is what's called an equivariant homology theory. So it's a homology theory, but for spaces with a group action. And so
I thought it's a cohomology theory. I mean, maybe it's not a difference, but
that matters. Well, sorry. In general, it's important to be precise about this, but right now, I think you can pass between them. And it doesn't really matter which one you think about, as long as you're consistent, if that makes sense. So, right, okay, yeah, it shouldn't matter which one you think about, but if you're careful about passing between homology and cohomology, it's fine. So, like I mentioned, there's this work of Charles Xiong, he has a couple different papers, some with other people such as Shiozaki and Gomi, where they get into why you should expect this to be true. And so, okay, what is equivariant homology? So equivariant generalized homology it's this, you can get into some quite nuanced things in algebraic topology, but we're going to ask for two things. First of all, ordinary homology is a homotopy invariant. So I'm going to ask that equivariant homology be preserved under equivariant homotopy equivalences. And moreover, I'd like to say that if I have a free action, then the equivariant homology should be the ordinary homology of the quotient. And so these two things determine it completely through something called the Borel construction. So Freed-Hopkins have another paper from 2019 where they use this perspective to classify phases with a spatial G symmetry in terms of equivariant homology for the same spectrum that you started with. So G acts trivially on the spectrum. If the following words are helpful, then I think it's important that I said them, but if not, no worries. That if you know about the difference between naive and genuine equivariant homotopy theory, or Borel and genuine, same word or same meaning, this is the Borel story, the simpler story. This is, maybe the people who care about homotopy theory and like its abstract categorical properties care about the genuine story, but fortunately, the one that we get is easier for computations. Okay, leaving that aside. So what Freed and Hopkins did is they said, okay, well, we care about, say, rotation equivariant phases on R2. Well, let's one point compactify so that we get something that's not trivial. And then ask, okay, S2 with that rotation action, let's compute the equivariant homology of that. And so what they get ends up being the correct answer. But there's a significant issue, which is that you might ask, okay, well, what if my rotation symmetry or my reflection symmetry mixes with fermion pairs? This is something that the physicists, condensed matter physicists, care about a lot. And the Freed-Hopkins approach does not address this. So this is where the genesis of my, like, this is why I, like, how this became my thesis, so to speak, is, in October 28, 2019, Dan told me, okay, well, we've got this paper and we'd like to check, we have this ansatz. We can, you like computational problems. How do you feel about checking whether this ansatz agrees with the computations the physics did? And so I said, okay, that sounds good. And we talked about a couple examples. And then he said, do you think you'll have this draft for me by Thanksgiving? Remember, this was 2019. And I said, yeah, of course. That sounds reasonable. So then, I did some digging and I pointed out that, okay, well, people care about this mixing. And it's just, we were both very confused about what to do with that for a long time. And so the paper ended up coming out on arXiv in February 2021. So it has not yet been Thanksgiving 2021. So I guess I'm okay. Anyways, the point is that this mixing is what made this into this like bigger question. So as an example, I'm going to compare internal symmetries by time reversal with reflection symmetries, which are spatial. And so this is an example where it's just Z2 acting and the physicists understand pretty well what's going on. So if time reversal squares to 1, purely internal, you get pin minus as your symmetry type. Okay, dimension 1, Z2, dimension 2, Z8, 0, 0. And this is exactly what the physicists predicted. If time reversal it mixes with fermion parity, you get pin plus instead of pin minus. And you get the pin plus, the Anderson dual pin plus borderism, which is in particular this Z16 in degree 4. Ah, shoot. This minus needs to be a plus. I'm sorry about that. So let's say that you care about a reflection symmetry, which doesn't mix with fermion parity. So now this is accounted for by Freed-Hopkins paper. And you plug in what they get and you get pin plus. And sure enough, the physicists think that you should get a Z16. But now, let's say that reflection symmetry mixes with fermion parity. So the physicists also know what we get. You get a Z8. But okay, what's going on here? We know that, so this part is just not covered by the Freed-Hopkins ansatz. We know that we have to get pin minus. I mean, look at it. But first of all, we don't know how to get there mathematically. And second, something changed. The classification looks the same, but pin plus and pin minus swapped. So what's up with that? So this is related to that work I mentioned of Dominic and of Ryan Thorngren, which is called the crystalline equivalence principle. So the table that we just saw suggests that the classification of phases with these point group symmetries should have something to do with the classification of phases with purely internal symmetries. So reflection is a point group symmetry, and it looks like the classification can be restated in terms of time reversal. But there's this twist. And so, okay, so physicists have known about this for a while, and this is this crystalline equivalence principle. So Thorngren and Elsa gave this physical argument for why you should expect this to be true. They focused mostly on bosonic phases, which are simpler, because the twist does not appear there as much. And for fermionic phases, it's weirder. They have a section where they talk about fermionic phases, and they say some good stuff, but they don't get to a general theorem or a general result. And neither had anyone else. There were more papers which considered more cases, but not a general theorem. So this is a good thing to. This is the yellow brick road that I would like to follow, because purely internal symmetries, we know how to deal with that from the perspective of invertible field theories. That turns into a mathematical problem that I like thinking about. So maybe getting to a crystalline equivalence principle would be a good way to be able to make computations. And so this leads to a question of mathematical modeling. So is it possible to mathematically model the invertible phases with mixed spatial symmetries in terms of some spectrum, or maybe some equivariant spectrum or something, with the following two desiderata? Is there a crystalline equivalence principle? Meaning, and does the model reproduce classifications already understood by physicists? So these are both kind of math questions. One of them is, I have a spectrum which classifies invertible phases with internal symmetries. And I have does my model that I produce have, do the homotopy groups that come out at the end, do they match as predicted by the crystalline equivalence principle? And second, let's say that I pick, reflection squaring to -1 of the F, or reflection squaring to -1. do I get the classification, those abelian groups that the physicists got? So those are the two things that we want to do. And so I think this is my last slide. Yep, this is my last slide, which says that, which is saying, okay, well, what happened in this? What did I do in this paper? So first, you have to mix fermion parity with spatial symmetries. And this requires generalizing from this particular spectrum to a family of spectra with G action. So you're working over Rn with a general space with a G action, and you have you have a sort of like a fiber bundle of spectra. Making this precise is a digression that I could get into if people want to know, but is a little bit involved. I mean, it heavily uses homotopy theory. And so now we can take homology. We can take equivariant homology, and we can take generalized homology, which is what we were doing with the Freed-Hopkins ansatz. But now, when we have a local system, you can take twisted homology. So twisted generalized equivariant homology is precisely the kind of thing that people like make fun of algebraic topologists for, like doing crazy categorical stuff that's like way out there. But I'll say a little more about why, like where the meaning comes in. So I called a particular twisted generalized equivariant homology group a phase homology group. And so this is what my ansatz for the group of phases is. It's the straightforward, like the generalization you would make of what Freed-Hopkins did if you spent enough time thinking about it. So in some sense, really, it's their ansatz. But a key part of what makes this run, I mentioned twisted generalized equivariant homology, abstract nonsense. But what makes this run is you say, okay, given the data of the symmetry type, the internal symmetry, the spatial symmetry, how they mix, you get out a particular local system of G spectra. And I think this is the kind of thing that takes you from very abstract to like something specific that gives this meaning, is how do you build this local system over space? And saying this takes a little bit of time, so I didn't want to put it on this slide, like how you get there. But the point is that you get a mathematical object, and then you take its phase homology groups, and then you get out abelian groups, which should classify groups of these point group symmetric phases or crystalline symmetry phases. So now you can ask, okay, do these match what I got out from this when I modify the symmetry as predicted by the fermionic crystalline equivalence principle? And indeed, it is a theorem that these things match. And so the way that I proved the theorem was essentially by computing, but sure enough, they match. And so you end up getting the switch. And then I didn't mention this on the slide, but I also did a number of computations where I said, okay, let's say I care about 2D or 3D point group symmetries. Not all of the point groups, but many of them. Well, what actually do you get out? And so that was an awful lot of fun doing some computations with the atom spectral sequence, the sort that Juvin and Joyan are very good at. And so I ended up getting in some cases, physicists had looked at it before and things matched. And in other cases, physicists had not looked at it before. And so we had predictions. Okay. So given that it's now 9:30, I should pause and stop.
Question.
Yeah.
Maybe you are going to summarize soon, but question about this. The first bullet point say the local system of spectral with G action.
Mm-hmm.
Let me make sure the G action here, G is the spatial symmetry you want to input as the G. And how do I think about the local system of spectra? Maybe in a more conceptual or down towards way.
Great. So
this is your contribution, right?
So are you familiar with local coefficients for like twisted cohomology and like the just ordinary cohomology, where you say, okay, well, I twist by the orientation bundle or something?
I certainly heard a word, but maybe you can still say it to all the audience.
Yes. Okay. Good. Sorry. Good point.
This is your contribution, right?
Right.
Yeah.
So I'd like to think about local cohomology with local coefficients. Let's say I have a space which is not necessarily orientable, like a manifold that's not necessarily orientable, and I could look at its orientation double cover. And so this is a space with an involution which reverses orientation, and the quotient is the original space I started with. So if I could say I care about cochains on the space above that, and how do they behave under this involution? If they transform as +1 under the involution, then they descend down to cochains on the space I started with, and I just get ordinary cohomology. So you could say ordinary cohomology is cohomology on the orientation double cover, which transforms as +1. You could also say, what if I transform by -1? And in general, that gives you something different. So you say, okay, I have this like cochains, but they change sign under the orientation reversal involution. And that gives you what's called like twisted cohomology when you work with that cochain complex. So you could think of this by identifying universal covers, or like by identifying covering spaces with things that have like, that's related to how, to representations of the fundamental group on something. And so you say, okay, if I wander around the fundamental group, what is the monodromy upstairs? So in some sense, I'm saying I have an orientation reversing loop in my fundamental group on the orientation double cover that now has monodromy -1. When I think about this, this family of, okay, I think I said that in the wrong order. I'm thinking of this orientation reversing loop acting on the integers by -1. And so what that says is when I go upstairs, when I reverse orientation, that loop is promoted to this involution. I want that involution to act as -1. And so I could look at other covers and say that, okay, I have this like this loop, and it is, it acts on the integers by something. Okay, and I want to say that my cocycles transform in that particular way under that action. So that's twisted homology. And so this is twisted generalized homology. And so the way that mathematicians have formalized this is due to Ando, Blumberg, Gepner, Hopkins, Rezg. So Matt Ando, Andrew Blumberg, David Gepner, Mike Hopkins, who is at Harvard, and Charles Rezg. And so what they did is they said, okay, we can think of this as sort of a family, ordinary homology, as sort of a family of copies of the integers over your space. And as you walk around the space, you walk around a loop, and that has monodromy on your family, on your thing that is kind of a vector bundle, but not literally. And so you act on, so that monodromy is telling you how you act and telling you how to get local coefficients. So we're going to say, okay, instead of the integers, I'm going to take a family of spectra. So in this example, what I did was I found a way to produce, given the data that I wanted for a mixed action, how to get a family of spectra. So you have some like total space-like object and a map down, and the fiber is this thing that Freed-Hopkins used to classify invertible phases. But if you wander around your space, there's monodromy. And so things get a little interesting because there might be higher monodromy. And instead of just saying fundamental group, you have to sort of consider the whole space. And that is a detail that I don't want to worry anyone about unless they want to worry about it. Juven, did this?
Yeah, thanks very much.
Okay, great.
Yeah, so the MTH of the H will be the internal symmetry you can still input, and G will be the action that associated with the spatial symmetry.
Mm-hmm.
And then usually the involution will be some Z2 action, but you have some way to grade it. Is that something like that?
To grade it? Well, it could be.
Yeah, grading in the sense maybe you can extend to some more complicated. Involution here is more like a reflection in physical sense. Is that right?
Yes. So you can extend to more complicated things, but that's not my work. That's a tale as old as time. Like cohomology, like ordinary twisted homology, that you could do more complicated stuff, and then I use that.
Okay, thank you. Thanks.
Yeah. So are there more questions since we got to the end of my talk? So are there, like, the rest of the remaining slides are quite technical and detailed, and since we've already been here for an hour and a half, I want to, if people want to hear about them, I can talk about them, but let's see what people have questions about. But yeah, thank you all for coming, and it's been great to be here. Are there more questions?
I think we all should first thank Arun for wonderful lecture. Thank you very much. Well, and thank you, Yini.
Thank you, sir. Thank you, Jeevan.
Yeah, thank you all for hosting me.
I mean, if other people have questions, I should ask. I certainly, I would, okay. Let's see, wait, sorry, I should look at my list of questions. Okay, you mentioned earlier in the talk that stacking gives like a literal tensor product on Hilbert spaces with Hamiltonians, but you mentioned that it's only sort of supposed that you get from that a tensor product on phases. Can you say more why you don't immediately get a tensor product on phases from that?
Great question. Yeah, sorry, I was a little bit imprecise. So what does a tensor product on phases mean? Phases are not vector spaces. How do I tensor them? So what I mean by tensor product is, secretly is a symmetric monoidal structure. Mm-hmm. And I would like to say that, phases form some sort of like symmetric monoidal category or symmetric monoidal groupoid or something. And then, mm-hmm. But we don't mathematically know what a phase is. So that's why I'd like to say that it works, but in the absence of a definition, I can't. But we do know that if you look at examples, then I don't know how to define stacking in general because I don't know how to define phases in general. But I look at examples of systems, I just take the tensor product.
Okay. And can you go back? I think maybe you already said this. Can you go back and say sort of what the obstacle is to giving a mathematical, to me as sort of maybe someone with a physicist's heart, the definition you gave of a phase sounds pretty precise. Can you maybe say more about why it's hard to turn into a mathematical definition?
So what is the space of Hamiltonians? So here's a reasonable question, which is, I think it's important for a topological phase that the space of ground states does not depend on the triangulation. It only depends on the underlying topological information. So you place your lattice on a manifold, and the space of ground states is a topological invariant. This is true in examples. But if someone hands you a Hamiltonian, how can you look at it and without solving it, how can you look at it and know whether that's true? Have you seen these like fracton systems?
No.
Okay, so this is absolutely wild. So you take this like nice, straightforward, reasonable generalization of the toric code in dimension 3. I mean, these are understood better now, but like when Zhangwan Ha and collaborators, I think they were the first people to do this. Someone let me know if that's not true. They wrote down this nice generalization and they said, okay, this should be a topological phase. Let's study it. And they got this bizarre behavior. You get particle-like things which are confined to, they can't move, they can only move in certain directions, like in a plane rather than in space. And you get a space of ground states that knows how big your torus is. So that's not great. Like a torus is a torus is a torus, as far as I'm concerned. Yeah. And it shouldn't be a torus of like area 30 or a torus of area 40. So somewhere in the part of the solution is being able to throw out those Hamiltonians. And when I say throw out, I don't mean fracton sum. People are very interested in these for good reason. But for coming up, I don't think they are topological phases, and whatever space of Hamiltonians has to sort of answer that question somehow. And I think no one has it. I don't know how to do that.
So you said so there's two problems with cutting out a space. How do I say this? I
think there's at least two problems.
It sounds like you said one of the problems is that you need to define a lattice Hamiltonian in a lattice independent way or something like that.
No, sorry. So this problem is that the space of ground states is lattice independent. But there's the first question of what does lattice Hamiltonian mean?
Yeah.
Which, I mean, okay, you probably have some ideas. But the big problem, I think, based on what Dan said to me, is like renormalization. Yeah. Like what happens when you make your lattice finer?
Right. In other words, if I understand right, sorry, I think it still sounds like what I tried to say back. So maybe I'm missing something.
Mm-hmm.
I had thought that one problem you said was that when you talk about the space of Hamiltonians, it's not like you're fixing a graph or whatever, or fixing a complex.
Correct.
And then looking at Hamiltonians on that, but rather you have some notion of equivalence for complexes. So you can refine and renormalize and whatever.
Mm-hmm.
And your Hamiltonian should really give you like a Hamiltonian or a class of Hamiltonians on
sort of
every one of those, a recipe for Hamiltonians.
Mm-hmm. So if you look at examples, then that's what happens is you have a way of saying, okay, I have a closed, I have a compact manifold with a triangulation, I get a Hamiltonian, I get a ground space. And so, so the question is like, how do you make sense of that? Like,
got it. Yes.
And I think that one is going to be easier than figuring out how to eliminate fractons. But honestly, I don't know.
I mean, I don't
Okay.
think that this is going to be too hard to formalize. I mean, I could pretty much write down what I think is the definition of phase. I think the difficult thing would be to prove that it has anything to do with TQFTs. I think that would be an incredibly non-trivial statement to go from these lattice Hamiltonians to TQFTs. And as you say, fractons show that that's not even true in general. So that would be the challenging part. But I don't really agree that it would be that hard to give a definition of phases on the lattice. It's just that it may be very hard to do anything with that definition.
Okay, this is good to know.
I mean, you still have to deal with the infinite Hilbert space issue, right?
Yes, but I think you can do that. You don't talk about Hilbert spaces. You talk about, you know, like functionals on the algebra of local observables and all that stuff that.
I see.
Yeah.
Oh, so then would you maybe get out something like a factorization algebra on the, you know, somehow?
Right.
Because those we know how to relate to topological field theories, at least to some extent.
Yeah, I don't know what a factorization algebra is. So.
Sorry, so the idea of a factorization algebra is it's a mathematical formalism for the algebra of observables in quantum field theory.
How is it related to TQFT? I mean, sounds completely general.
There's a notion of a locally constant factorization algebra, which, I mean, you know, topological field theories ought to have locally constant algebras of observables. And someone proved, I should know who this is. It might be Jacob Lurie, but it might be Costello and Gwilliam or someone else, that these are equivalent to something called an EN algebra. And then an EN algebra can give you a topological field theory. So it's not directly like, okay, given a factorization algebra, okay, I know that I have the Levin-1 model or whatever. But there are theorems that that say things like, okay, you know, here's how we use factorization homology to get out topological field theories. So Liang Kong has a paper about this, I think, as does a grad student at Stoneybrook